Feels like so much preamble, but now we're here, we're at derivatives, we're starting our differential calculus. It'll all tie in, but now we can at least say we're learning about derivatives. There will continue to be a lot of graphs in our life. That's just the nature of calculus, but here we go. So we're looking at a graph here, and we can see that the y-axis is velocity and the x-axis, the independent variable, is time. And when you graph velocity versus time, what you end up with is acceleration. And this blue line represents an acceleration of something. You can see sometimes it's positive, you're getting faster. Sometimes it's negative, which means you're slowing down. And it has a couple of stop points as well. Now we've thrown some lines on here. The red line is what I call a secant line, and it will connect 2 points on a graph. So you can see I've drawn a point here and a point here, both of which are on this function. And when I connect them with a straight line, I'm making a secant line. We'll talk about that first. And then we're also going to talk about the green line, which is what we call a tangent, not like our trig ratio. Of course, we're using the same thing. This is like going out on a tangent. So it's a line that, when I think about a point on the graph, it's only touching the graph at that point. So looking at our secant lines, we can see that it's calculating an average slope between 2 points. I mean, we can be slightly alarmed because obviously as we go down up, our slope is changing a lot, and that's part of the calculus of this. But we can certainly say between, let's say, point x1 and point x2, at x2 rather, that the red line is going to represent an average slope. When we say average slope, we are saying average rate of change, and that's where you'll start hearing me say things like AROC and IROC. So when I say AROC, I'm referring to the average rate of change. I'm talking about a secant line. And because this really is just a slope between these 2 points, remember this from last time or last semester, we're talking about rise over run in order to find an average rate of change. So we can use our slope formula, which was y2 minus y1 over x2 minus x1. We can make it slightly fancier by making it f of x2 minus f of x1 divided by x2 minus x1, but it's the same thing. So how could this have an application? Well, I have a velocity to time graph, which means I'm talking about acceleration. So if I want the average rate of change over this time, then I'm going to get the average acceleration. So if we look at this graph, I didn't draw it very well, but let's assume our go-karter started from 0, 0. And, went faster, went slower, went around curves or whatever, but 120 seconds later, this is where the go-kart was. And when I add that secant line in from time is 0 to time equals 120 seconds, there's what I get. And if I want to find the average acceleration, I'm finding the AROC, and my math is pretty straightforward. Or I'm just finding the slope. F of, x2 minus f of x1 over x2 minus x1. And that will give us an answer of 0.19 meters per second divided by seconds again, meters per second squared, a unit of acceleration. So that's the average acceleration. But as I look at that blue line, the average acceleration does not tell me very much about the trip. There's a lot of other stuff going on. Bring in the tangent lines. We said with the secant line we could get the average acceleration between 0 and 120 seconds. But what if we want to know what's going on at a certain time? Like, what is the acceleration exactly at this point? Or what is the acceleration exactly at this point? That's a little more complicated. How can you find the slope of a line at a single point when you always have gone around finding slopes by using 2 points? So if we wanted to find the slope at exactly 120, what can we do? we're going to use our tangent line because it touches only at one point. So if we think of when x is equal to a, this is f of a, what that graph is doing at that point. And if I want a tangent line, maybe I'm going to use a tool, hold on. Not so great, but ideally what I'm drawing there, not very well, is a line that is just touching my green graph at one point, right when x is equal to a. And why do we do that? Because if we get infinitely close, if we zoom in onto x equals a, we're going to have something like what I've got in the little inset here. As you get really, really close, from far away I can tell this is part of parabola. That line is curved, but when I get really, really, really close, I can make it look like a line. So in theory, I can find another point really, really close, and then I can use my slope formula. And when we calculate the slope of a tangent line, using that one point but making another point really, really close, what we're doing is we're thinking about the IROC, the instantaneous rate of change. So that's the other one I use. So IROC for tangent lines. So our slope of our tangent is equal to the instantaneous rate of change. And whoa, limit, hello, here we are. Okay, so as x gets closer and closer to a, very infinitesimally close, we're finding the slope of the tangent. And we have f of a minus that f of x, which is very, very close as x approaches a, divided by a over x. So that's y2 minus y1 over x2 minus x1 in disguise. And we bring it closer and closer to that point A. Look at our rate of changes with an example of water slide, super fun. Okay, so we have a water slide, and we have a formula for its height from the start of the water slide to 7 meters along the ground. That's the 0 is less than and equal to x, which is less than and equal to 7. So the first 7 meters of run along the ground, the shape of that water slide, or the height, I guess, is being modeled by this equation. All right, that's a gross equation. But first we want to know what the average slope of the water slide between 4 meters and 6 meters is. How could we do this? Well, we have our AROC formula. It equals f of x2 minus f of x1 over x2 minus x1. So a little bit of work on the side. F of 6 is equal to 8 over 6 plus 1, and this is just me taking the formula. F of 4 is equal to 8, oh, who picked this? It's terrible. Over 4 plus 1. This was my bad doing because I can't math. And we're going to get some numbers. So 8 divided by 7 gives me, this is obviously a homemade problem because it's very, very short. This is the kiddie water slide, 1.143 meters. And then when we have 4 meters, we are going to be only at 1.6 meters. So a slow start to this water slide. And then this all goes into our formula. We're going to have 1.143 minus 1.6 divided by 6 minus 4. This is going to give us negative 0.23, which is our average rate of change, our slope when you're between 4 meters and 6 meters along the ground. To look at the IROC, we know that our formula is going to be the limit as x approaches a, f of a minus f of x over a minus x. So in order to compute this, we're just going to have to pick something, an a value, or sorry, an x value that's really, really, really close to our a value, let's call that a, of 5 meters. Okay, so that's up to you. That's arbitrary. Do you want to do 5.01, 4.98, 5.001? Let's use x equals 5.001. Time to do some calculating. So I'm saying that a is equal to 5, so we need to know what f of 5 is, which is simply 8 divided by 6, and I'll give it some accuracy there. And finally, I'm noticing that I have used f instead of h, whatever. And then let's find out what's happening when x is 5.001. So I'm going to end up doing 8 divided by 6.001. And, you know, throwing away some accuracy for the sake of writing it down, I get this. Okay, so our IROC is going to be f of a, 1.3333 minus f of x, 1.3331 divided by a, 5 minus 5.001. So that's how we've got that limit. We've gotten to a point where we're only 0.001 units, or meters, I guess, away from that point we're considering 5 meters along the ground. And when you do this math, you get negative 0.2. And we can observe that at 5 meters along the ground, we're actually pretty close to the average slope between 4 and 6 meters. That happened to work out that way. That is not always going to be the case. That's a lot of work. And it requires you to arbitrarily pick a point that is as close as you feel it needs to be to your point of interest. So we need something better. So we're going to rejig our equation so that it simplifies before we deal with numbers. Okay, and it'll take away that arbitrary choice that we have to make. So we're going to change things up a bit. We're going to introduce a variable h, and it represents the change in x, and that's the distance between x and a, so how far away you are. So we're going to take our original limit equation and we're going to change it to the limit as h approaches 0. So as we get closer and closer, another way of saying it, right? As the distance or the change in x between x and a comes down to 0. And then we can rewrite our equation like this, where we're taking f of the function of x plus that little bit as it gets closer to 0 minus y2 f of x. And then we have x plus h minus x. And we actually get a little pre-cleaning that happens. So we have this formula. The limit as h approaches 0 of f of x plus h minus f of x divided by h. And we call this the equation that we use to find a derivative from first principles. Okay, I put our little formula right here for reference. And here we go. So remember, we're not, even though they've given us x equals 1, we're not going to use that till after if we need to. So we've got an equation, g of x. So I need g of x plus h. And all you do to make that is replace the x with x plus h. And when it's a nice little equation like this, it works out, it gets uglier. And of course, we know that g of x is negative 2x plus 7. So we're going to put that into this formula. We'll leave the limit as h approaches 0. And then we have, and I'm going to do some simplifying, I'm going to distribute that negative 2. So I have negative 2x minus 2h plus 7, and that's g of x plus h. And I have minus, maybe I'll do it a couple steps here, minus 2x plus 7. And all of that's over h. And you might be freaking out a bit and being like, well, you know, that's an h on the bottom. It's going to be indeterminate. Don't worry, don't worry. It all works out. It all works out. Now, I've got minus minus. So notice this. I've got negative 2x minus minus 2x, which is negative 2x plus 2x, so those cancel. I have a negative 2h. And then I have positive 7, and I'm going to have minus 7. So that's going to be 0 as well. And you're like, well, still a problem. But is it really? Because you've got h over h, and those can cancel. And suddenly, your limit, as h approaches 0, is negative 2. And does it matter if you're at x is 1 Or if you're at x is 5,000? No, because there's no x in that formula. So why does this make sense? Well, g of x was a straight line. It's going to have the same slope everywhere. In fact, we can tell from the equation that the slope is -2, so this seems like a lot of extra work. In fact, it's a good introductory example. So let's move on to something a little more gnarly. This time they want me to find the slope of a tangent line. Am I doing anything differently? No. Instantaneous rate of change, slope of a tangent line. These are all our derivatives. Okay, so I have f of x. I'm also going to need f of x plus h. I'm going to go pink. And remember, that just means every x becomes x plus h, which is a giant pain in the butt, but works out if you're good with your algebra. Okay, so let's clean this up. We're going to have 3. Remember that x plus h expanded is not just x squared plus h squared. You should know that by now. Minus 4x minus 4h. Oops, I gotta bring that out. Plus 5. Okay, a lot going on there. And we are finally, I'm just double checking, 3x squared plus 6xh plus 3h squared minus 4x minus 4h plus 5. There you go. Beauty. Ready to go into the formula. Okay, so we have f of x plus h. I'm going to write it in this color now. 3x squared plus 6xh plus 3h squared minus 4x minus 4h plus 5. And we need to subtract f of x. So change the signs of everything there. Minus 3x squared plus 4x minus 5. All of this is going to be over h from our formula, and we're thinking about the limit as h approaches 0. Okay, this looks like terrible, but notice what's happening. Everything I highlight will cancel. 3x squared minus 3x squared minus 4x plus 4x plus 5 minus 5. So those are all gone. So it's getting a little better. And let's see what we're left with. Right now, I have 6xh plus 3h squared minus 4h all over h. And we're still thinking about the limit as h approaches 0. This is not great because that gives me a 0 on the denominator, but maybe I can do some factoring on the top. I can pull out an h, it's common to all terms, 6x plus 3h minus 4. All of this still over h. Now these cancel. So I'm looking at the limit as h approaches 0 of 6x plus 3h minus 4. And we've only got one h. If we make it 0, it's 6x plus 3 times 0 minus 4. So our answer, our slope of our tangent line, is going to be 6x minus 4. So now we have to go back and see what's happening when x is equal to 2. This equation, 6 times 2 is 12 minus 4 equals 8. I'll put that over here. 6 times 2 minus 4 equals 8. And maybe make that look more like an 8. It's a lot of work. So we did all that work to find the IROC, the slope of the tangent line. What we're finding is the derivative. What differential calculus finds? Derivatives. So a derivative is going to look at the change in your vertical, your dependent variable, with respect to a change to an independent or a horizontal, your x-axis variable. We figured out that we can use a limit formula in order to find that derivative. If our function is a straight line, our derivative is just going to be a constant. That's easy. But if our function has any curves going on, then we get another function as a derivative, and we can find what's happening at certain x points by subbing that x value in to our derivative formula. And we call this finding the derivative using first principles. So remember that, because you might see that on a test sometime. So now we kind of know what derivatives are all about. They're just finding the slope at a point on a graph, which happens to be the same as finding the slope of a tangent line to a point, which happens to be the same as the instantaneous rate of change. They're all the derivative, and this is our first principles formula, a limit formula. Now, we're going to get some formulas and some rules that are going to make our life easier. We're not going to take every function and do this much math to find derivatives. That would be too time consuming. But know that this is where it comes from and that you are responsible for being able to get a derivative from the formula, the limit formula. Okay. And this is kind of a tacked on thing. When we get into this, we're going to see a lot of different kind of notations for derivatives. A lot of people have their own style. So we have fancy notations. The change in y with respect to the change in x, dy dx, which is really, rise over run. That explains a lot. We use a prime, and this is lazy and quick. I like it. To also say that if we have a function y, then our derivative of that function will be y prime, which is y apostrophe. We say y prime. I'll write that one down. Y prime. And then sometimes, if you like the function, you might say df dx, because of your fancy pants. And then you might be a person that also puts that prime, f prime of x, in the middle. They're all the same thing. And just kind of some summary points that bring together limits and continuity. We will differentiate and we will find derivatives. That's what we're going to do for the rest of this course. If you can differentiate, if it works out, like you don't get a 0 on the bottom, then the derivative exists. And in fact, continuous functions are almost always differentiable. They have derivatives. However, if you have a vertical line, like a function that goes like this, there is no derivative. How come? The slope of that line is undefined, right? Rise over run. You're going to get a fraction over 0. Or a cusp or a sharp corner, like an absolute value graph, will not have a derivative at its point because the slope is changing too drastically from one side of that point to the other.